Hello, I'm Zurab Ugulava, and today I will represent Team Georgia with problem number 6, Saxon ball. As the problem indicates, a ball with a hole in space would sink when placed in water, and I had to investigate the parameters that determine the time of sinking. My general observations will be about the motion of the ball, its stability as a system, and validity as a clock. And I will investigate relevant parameters such as size of the hull, density and viscosity of the fluid, and the ball parameters. First of all, I investigate the flow rate inside the ball and its total fill-up time. After that, I will derive equations of the motion and verify them with experiments. And I will also check validity as a clock. And finally, I will investigate viscous effects. When the ball without a hull is placed in water, the acting forces on it are nullifying each other. But as it has a hull, when we submerge it, there is a pressure difference and water starts to flowing inside the ball. We get the additional mass, so we get the additional weight, and when this force outweighs buoyant force, the ball will start to sink. Well, my experimental setup simply consists of the large water tank, the ball with a hull, and recording device. I calibrated my software on underwater tiles and I tracked the lowest point of the ball to avoid any extra optical errors. And as you can see in preliminary observations, ball might not sink, it could sink halfway, or it could sink completely. To explain such cases, I want to introduce I want to in, I want to introduce some subtask of the tightly sustained ball, and with simple substitutions in Bernoulli equation and the continuity equation, we could get the equation which could describe the water level inside the ball through time, and for such balls it gets such form. As you can see, it's quite a good match with the experiments, and if we integrate this formula on the screen, we could even get the total filling up time of the ball. But that's not enough to describe phenomenon fully, and to fully understand it, we will have to add equations of motion, which are derived from Newton's second law. And solving this set of differential equations could obtain us sinking time. When the levels inside and outside the ball are equal, there is no more pressure difference, so there is no more inflow. Further motion solely depends on the density of the ball. If its density is less than water's density, it will just float, otherwise it will sink like just full object. Now let's analyze data. First of all, I attach this ball to the force sensor and measure the total acting force on this ball. And as you can see, it rises through time. That means that our assumption that we have the additional mass effect isn't wrong. And you see there vertical vertical position dependence on the time and for different densities, and as you can see, these points are the exact points when the water level inside and outside ball are equal to each other. But I think that it's more interesting case when the total acting force on the ball is null. Well, we get the constant speed of the ball and it submerges linearly. And I think it's more interesting because we get the easier ball to calibrate it clockwise. Well, This is a graph submerging time depends on the hull radius, and as you can see, the larger the hull, the more surface it has the more inflow, so more weight, and it's easier to submerge this ball completely. And we also varied the initial mass of the ball, attaching neodymium magnets to it, and with extra load we get the extra weight, gravity force acting on the ball, so it gets easier to submerge this ball completely. Well, I also investigate the water level inside the ball, and as you can see, the starting point is weirdly out of the range. Well, it's happening because the initial flow isn't really stabilized, and this area of the time it needs to get stabilized, and it follows the linear motion afterwards. Well, everything was going to according our theoretical model until we changed the thickness of the ball. Well, when we get the thick balls, water experiences some friction forces acting on it inside this little hole, and we have some viscous effects. When water near the wall surface has less velocity than in the middle, so we get kind of profile, and to describe this profile we wrote Navier-Stokes equation, and the incompressibility of the water, and we obtain the profile of the water, which is dependent on the pipe length, hull radius, viscous coefficient, and fluid density. If we average this profile through the whole area, we get the mean velocity with which water flows inside the hull. With that, we can get the inflow equation, and when we solve it for the different surfaces, the larger the surface, the quicker the process. And if we combine it with the motion equation, we could also explain the deviation we got initially with these thick balls. Well, when the normal ball is put in the water, initial gravity center and buoyant center aren't aligned perfectly, so it gets inclined. But when it has a hole, it starts to filling up, so the center of gravity gets lower, it gets torque to turn, it gets resting torque, and turns this ball vertically. And with this torque equation, we could obtain the critical angle with which, if we put this ball in the water, it could not fall over. And this is experimental results, and as you can see, it's quite a good fit, and the larger the ball's mass, the less the inclination, and more precise the clock. And at a certain value, there will be no tilt at all, and in our experiments, it was conducted in such way. And finally, I want to talk about the surface tension effect. As you can see, the ball is just floating without submerging at all. The surface tension forces are actually nullifying this gravity force, and we can obtain the critical mass of the ball, which can possibly this water surface hold. And here also you can. So surface tension might prevent the phenomenon, and as you can see, we also calculated calculated the critical mass for our given conditions, and you can see this nice three-dimensional graph for both coefficient dependence. And finally, I want to conclude. First of all, we explained the phenomenon with Archimedes principle and additional mass effect, and we described the moment system and derived motion equations using this subtest of the tightly inbound ball. And we got the inflow equation, we added the Newton's second law and got the motion equation, and we derived it for the several cases for different densities. And we also explained the viscous effect and its deviation. The larger the thickness, the larger the thickness there is, it prolongs the sinking time. And we also investigate the critical mass, which can this water film possibly hold. This is my reference bibliography, and thanks for attention.